All right, so in the next few videos, we are going to be tackling many examples regarding the electromotive force induced inside a closed loop, okay? So as mentioned before, to find the electromotive force, we calculate the change in the magnetic flux. There's three main ways to achieve this. We change the magnetic field inside the closed loop, we change the area of the closed loop, or we change the angle between the area vector and the magnetic field. So we are going to do many problems, and at the beginning, the first few problems, we're going to be solving a change in magnetic field, then a change in area, and finally a change in the angle between the area vector and the magnetic field. So this example, question 221, we are going to tackle a case where the magnetic field is changing. All right, let's read the question. Question 221. The square coil has side I is equal to 0.25 meter long and is tightly wound with N equal 200 turns of wire. The resistance of the coil is R is equal to 5 ohm. The coil is placed in a specially uniform magnetic field that is directed perpendicular. That's really important. That means the angle is 90 degrees between the magnetic field and the coil and 0 degree between the area vector and the magnetic field. Okay, so the coil is placed in a specially uniform magnetic field that is directed perpendicular to the face of the coil and whose magnitude is decreasing at the rate of the derivative of the magnetic field with respect to time is equal to minus 0.04 Tesla per second. Okay, so let's have a look at the diagram here. We have a square coil with 200 turns. It has a resistance of 5 ohm. Each side have a length of 0.25 meter, so we can easily find the magnitude of the area. It's 0.25 square in this case, and we're told the change of the magnetic field. All right, so to the part A, we are asked to find the magnitude of the EMF, the electromotive force. And the magnitude can be found by the number of turns multiplied by the derivative of the flux with respect to time. Now note, in the summary, there was a minus in front, and this minus is only useful in finding the direction of the current induced. All right, so again, just like we did in the previous chapter, ignore that minus. We have to look at the diagram to determine in which direction the current will be induced. All right, so let's replace the formula for the flux with the formula we know, which is the magnetic field multiplied by the area multiplied by the cosine of the angle between these two. Oh, there's an N missing. I'm gonna add it over here. Now note, in this problem, in all the problem we are going to consider, only one variable will be changing at a time. All right, so there won't be like area and magnetic field changing at the same time. Only one at a time. In this case, the magnetic field is changing, the area is constant, the angle between the two is constant. So we can extract these two, and again, there's an N missing over here. There we go. So, and the number of turns also is constant. That one is fairly obvious. So we extract these one and we are left with the derivative with respect to time of simply the magnetic field. Well, we have been given that value. It is the minus. Now note, this minus also indicate the direction. It tells us that the magnetic field is decreasing, and we have to take an assumption for this problem. I will talk about it in part B of this problem. All right, so at this point we have all the value. We are already told the derivative of the magnetic field with respect to time. We know the number of turns, the area, well, it's 0.25 square. Cosine, we already said that the angle is 0. Now note, there's an angle, so this is the magnetic field, this is the coil. There's an angle of 90 degrees between these two. But from the point of view of the surface, the area vector is a vector that is also perpendicular. So in both cases, these two are the area vector and the magnetic field have an angle of 0 in this case. All right, so we input all these values, we get an electromotive force of 0.5 volt. All right, now in part B, let's read part B. What is the magnitude and direction of the current circulating through the coil? So let's solve the magnitude of the current. This is the easiest part, and then we are going to be talking about the direction of the current. So to find the magnitude, we simply use Ohm's law. So the current multiplied by the resistance is equal to the voltage. Well, resistance is 5 ohm, voltage is 0.5. If we isolate the current, we get 0.1 amp. That's it. Now, for the direction, what we need to know is in which direction is the change in flux pointing. The magnetic field is pointing downward. But what's not obvious is that the magnetic field is decreasing. It is getting lower. The number of field lines going through the loop and pointing downward is decreasing. What that means is the derivative of the flux with respect to the time is pointing up. All right, so the change in magnetic field is going up. What that means is there will be an induced magnetic field inside the coil that resists this change, okay? And this magnetic field will have to be pointing down. So I'm gonna call it B induced, and basically there's no value here, but the magnetic field is being induced and is pointing downward, opposing the change in magnetic field. Well, if the induced magnetic field is pointing downward, we curl our finger to know the direction of the current. The current will be going in that direction, which is clockwise. So by the way, I'm gonna write CV for clockwise, and CCV is counterclockwise. All right, so from experience, I know finding the direction of the current can be confusing. We are going to be solving many examples, but if you get stuck here, let me know. I'm here to help you. I will help you clarify how to find the direction of the current, and I can guarantee you that you will have a question asking you to find the current in the direction of the current of an induced current. All right, for sure you will have one such question on the final. All right, so we are done with question 221. Let's switch to another question now.